All right, thanks everybody. So in the last lecture, we defined what the class is about, and we defined this task of generative modeling. And if you remember, we accepted the different terms in the title of the course. We call this probabilistic and deep generative modeling. And we try to explain why it's probabilistic, why it's deep, why it's generative. So in this lecture, we're gonna go deeper into each of these terms. Part of the lecture is going to be a review of certain things in probability and generative modeling. And then I'm also going to set the stage for why we're going to be doing all of these advanced machine learning techniques. Why are we going to be covering these advanced methods? I'm going to give you a few simple examples of generative modeling and show why some of them are easy and why some of them are hard and why they require sophisticated methods. And then in the next lecture, we're going to see our first family of generative modeling algorithms, of deep generative modeling algorithms, which are going to be autoregressive generative models. But for now, first a review of probability and some concepts in machine learning, and then defining the generative modeling problem, and defining a few classical approaches, and showing why they might not work, and why we're going to need all of the things we're going to do in the next lecture and all the following lectures. So that's the plan for today. And before I start diving into the details, I have this slide which is kind of an overview of how we define the task of generative modeling in the last lecture. Here, if you remember, we're going to be, so our goal is to build machine learning models, machine learning algorithms that can generate things and can do other manipulations over high-dimensional objects, such as images. And the way that we're going to do this is going to be different from how other fields of computer science do it. For example, in computer graphics, someone might implement by hand a complicated graphics engine that can render in various types of scenes. That's one approach, which involves a lot of engineering. Our approach will be based on machine learning. Instead, we're going to be taking a large data set of the objects that we want to model. In this case, these are, here I have a data set of images of dogs. We're going to learn that generator, we're going to learn that system purely from data. And in particular, what does it mean to learn? Learn here means that we're going to be defining a probability distribution over these images. So this is called, well, these are statistical models, so we learn from data. In particular, the definition of what it means to learn from data is to define a probability distribution over each image, or over all the images. We're going to have a probability distribution that assigns a higher weight to better images, lower weight to other images. And then once we have this probability distribution, we're going to be able to solve a lot of interesting tasks. We're going to go into much more depth about each of these tasks, but for now, generation is the first example, the first task that you can think of here. We can sample from the distribution. So if we have P of X, we can draw X's from P of X. We can draw new images. That's obviously an interesting task. We've seen interesting applications of it in the last lecture. And there's other tasks that we're going to be going through in more detail throughout the course. Another one, which I alluded to in the previous lecture, is representation learning, which means that I am not just interested in generating these X's, but I'm interested in discovering in an unsupervised way something interesting about the images. Maybe there's some patterns or some classes of images that are present. I want to discover this from data. That is some of the things we might do using a form of representation learning. So this is our goal. This is an overview of what deep generative modeling is. But in order to do all of these things, we have to start at step one. And step one is going to be deciding what does it mean to defining what it means to represent a model as a probability. If you remember, in the last lecture, I had this outline of what a generative modeling algorithm looks like. And it involves three components. And I would also say every machine learning algorithm has these three components. And these components are the modeling, the defining the model family. In this case, our model families are always going to be probability distributions. So we have to define the class of probability distributions that we're going to work with. Then we're going to have to define a learning objective and an optimizer. When we have these three things, we have a complete machine learning algorithm. But for now, we're going to start at step one. We're going to try to define a model, define a probability distribution over images, and then later we're going to look at how we can learn this distribution. Okay? And so the plan for the lecture, again, we're going to start by looking at what it means to define a probability distribution. What are some different types of probability distributions that exist? So that's going to be the first maybe half of the lecture. And then in the other half of the lecture, I'm going to do a bit of review on discriminative and generative models. Let's just remind ourselves what's a classical generative model. And then we'll end with a first example of a deep generative model. So it extends these classical generative models to the deep setting. We're going to be parameterizing them with neural networks, and we'll see a first example of what that means. That's the plan. Okay, so as a warm-up, let's first just look at a few really simple examples of what we could use as a probability distribution in some really toy settings. In fact, here I'm starting the slide with maybe the simplest distribution you can imagine, which is the Bernoulli distribution. We should remember this because this is going to be a building block for a lot of things that are going to come next. But a Bernoulli distribution is basically a distribution over a coin flip or over two possible outcomes. Let's say that our data can take only two possible values. We can give them arbitrary names, 0 or 1, or heads or tails, but there's only two things that can happen in the world. And so a Bernoulli distribution is a distribution over these two possible outcomes. And all that it does is to define the probability of one outcome. Let's say we're modeling heads or tails, or whether a coin falls heads or tails. So we're going to say that the probability of heads is going to be some scalar p between 0 and 1, and then the probability of tails will be automatically defined to be 1 minus. And so we write this as x tilde Bernoulli of p. X is a random variable that's sampled according to Bernoulli distribution. And again, our example here is a coin flip. So this distribution only has a single parameter, and that is p. Okay, that's something that you should have seen before. Very simple, very simple example. Our first example that will be used as a building block for what comes later. Now, one way to make this just a little bit less simple is to go from a Bernoulli distribution to a categorical distribution. A categorical distribution is like a Bernoulli distribution, but instead of having two outcomes, you have some number here, m, lowercase m, of possible things that can happen in the world. So one example of a situation you could model with a categorical distribution is throwing an m-sided die. So let's say a regular die will have 6 sides, then you have 6 possible outcomes. You throw the die, you observe one of the outcomes, and maybe the die is not fully balanced. So you would want to model all the possible outcomes with a different probability. And this distribution has m minus 1 parameters. The way this distribution is defined is by specifying a probability to each possible outcome. And because we have m outcomes, well, because we have m outcomes and the probabilities have to sum to 1, there's one redundant degree of freedom, so it's enough to define m minus 1 numbers between 0 and 1. And then the other one will be 1 minus that. So there's this distribution has m minus 1 freedom and m minus 1 parameters. Okay. So two simple examples. Now let's make this one step more interesting. Here, so in the previous examples, we had these. We just had some kind of categorical variable, maybe a 6-sided die. Let's say that now we wanted to model something a little bit closer to our initial motivating example. Let's say that we wanted to model pixels in an image. And let's say that we just wanted to model a single pixel. let's say that we're modeling images, and those images contain a single pixel. Okay, so we're modeling one by one. We're building a general model over one pixel images. So what does it mean to model a pixel? First of all, what's the set of possible values that a pixel can take? So a pixel is defined by three values: the intensity of the red channel, intensity of the green channel, and the intensity of the blue channel. And in most examples, we would have 256 possible. So these are often encoded from 1 to 256, or from 0 to 255 on a computer. So there's 256 possible values that each of these values can take. And so each pixel can be defined as a tuple of the R value, the G value, the D value. So it's defined by three numbers, and each number is an integer between 0 and 255. So that's how we represent a pixel. And now we want to define a probability distribution over all the values that this pixel can take. So how would we do this? Well, we can model this using a categorical distribution, right? We have a finite number of outcomes. In fact, we have 256 outcomes, 256 possibilities for R. For each of these, we have 256 options for G. For each of these, we have 256 options for B. So we have 256 to the power of 3 possible value. So the pixel can be in 256 to the power of 3 possible states. So here we have a categorical distribution where m equals 256 to the power of 3. And one way to view this is this kind of three-dimensional cube or three-dimensional table. Here for each, so the value blue can take, the blue channel can take some number of values, the red channel, the green channel, and for each combination, there's a color for the pixel that's illustrated in this cube. And so if we wanted to specify a probability distribution, we have to assign a number to each entry of this cube. Or in other words, you can think of this distribution as being defined by a three-dimensional table of numbers, right? So defining a categorical distribution over a single pixel means defining a 256 by 200. It means filling in a three-dimensional table that's 256 by 256 by 256, and that's this cube, right? So now we can view the problem. We can view the task of modeling a one pixel image as filling in this, as defining this three-dimensional table of the probabilities that the pixels contain. And if we wanted to then sample a new pixel, well, we can sample from a categorical distribution, right? So if we have a good distribution, we can then perform the generation task by sampling a pixel from this categorical distribution. And now we have, assuming we can learn this, we have a simple general model over one-dimensional images, or pixels. Okay. And so again, how many parameters do we need to specify this distribution? It's 256 to the power of 3 minus 1, because this is a categorical distribution. We have 256 power 3 outcomes, and we need that minus 1 parameters to define this distribution. So now we have a distribution over pixels. And let's now take this one step further, and let's try to define now a distribution not over pixels, but over images, which are arrays of pixels. So now we're going to try to define a distribution over not 1 by 1 images, but 28 by 28 images. And to make things simpler, let's instead of thinking of images that are in color, let's look at these black and white images. And let's say that we're trying to model these kinds of digits. So this is a handwritten digit. It's a 28 by 28 pixel image, and the values are just black and white. Okay, these are samples from a famous data set in machine learning called MNIST, and each data point here is an image. It's 28 by 28, and it's black and white, so it's a 28 by 28 array of zeros and ones. Okay, and let's say now we wanted to take the same approach to define a distribution over images. Right, so now we're gonna define a distribution over these over n pixels, and here is 28 by 28. So defining a distribution over images means defining a distribution over a vector of n binary pixels. Okay. So how many possible states can a single image have? If we take one image, how many possible values can this take? An image is a 28 by 28 array of zeros and ones. How many possible values can that? How many possible images are there in the universe? So for each pixel, we have two possible values. So for the first pixel, we have two values. Then for each assignment of 6 pixels, we have 2 assignments. The second pixels, then for each joint assignment, we have 2 assignments to the third pixels, etc. So we have 2 times 2 times 2. We have 2 to the power n possible images that exist. Okay. So if we wanted to do this, if we wanted to now build the same type of model like we did for a single pixel, we have to, here, our naive approach would be to define a categorical distribution over a one-dimension, over these 2 to the n possible states, right? So if we were to do exactly the same thing as we did with one pixel, and we consider the states of the states that are modeled using a categorical distribution, if we consider that to be all the possible images, then we have 2 to the n states that we can model. So m is 2 to the n. So a categorical distribution that models these images requires how many parameters? Well, m minus 1, right? So it's 2 to the n minus 1. Okay. And this is a problem. And in fact, I want to emphasize this is the main problem of generative modeling, and this is the whole reason why we have several months of lectures on this. This is bad. So if you have something that's exponential, there's no way that you can model this in practice. Even with 28 by 28, that's 2 to the power 768. That's more than the number of atoms in the universe. So it's not possible to define. It's not possible to list. Like, it will take you more than the time of the universe to just enumerate all the possible parameters that this categorical distribution would take. So it's not possible to specify such a large number of parameters even for n of this size. And yeah, and it's more complicated for even more realistic images. This is why it's called the curse of dimensionality. There's a question.
I guess it does make sense for images, but I'm assuming that sometimes these variables can be independent, and so that would reduce the number of parameters by a lot.
Yeah, that's a really great observation and a really good point. And let me just, well, actually, most of my slides will be an answer to this question. So let's look at that, and then you can ask a follow-up question if that doesn't solve. If that doesn't address, just mention. Okay, so again, I just want to emphasize here, this is called the curse of dimensionality. If you do this naive approach requires a number of parameters that grows exponentially in input, that doesn't scale, and that's why we need all of this material, all of these lectures to solve this problem. So obviously, this naive approach doesn't work off the top of, but yeah, this naive approach doesn't work. Just modeling this as a simple categorical with 2 to the n states, that doesn't work. What else could we do? Well, we get to choose the model that we learn here, right? We get to choose the probability distribution that we use to fit to this data. So we can make any assumptions we want to this distribution. And one assumption that we could make is, as you mentioned, we could assume that it's independent. I think in your comment, you were saying that the data might be independent, which is also true. But for now, this is just a modeling decision that we get to make. We can fit whatever distribution we want, right? So let's just fit one where all the pixels are assumed to be independent of each other. So now I have each of these pixels, x1 to xn, is a binary variable. And I will assume that the joint distribution is defined as a product of distributions over each pixel. Since each pixel is binary, P of x1, P of x2, these are all Bernoulli. So let's assume that this is the model that I will try to fit to my data. How many parameters does this have?
N.
N, right? Because I have n probabilities, each of them is a Bernoulli. A Bernoulli has one parameter, so that's n parameters in total. But sorry, I guess I should have asked the other question first. How many states, how many possible assignments, how many possible joint assignments are there? How many possible images exist in the world? Still the same number, nothing changed. The real world hasn't changed. We still have 2 to the n possible images that exist out there. But how many parameters do I need to specify this joint distribution? Well, I need one parameter for P of x1, and therefore I need n to specify the whole thing. So we can have a distribution over 2 to the power n images with only n parameters. Now, of course, this is a strong assumption. If we fit this distribution to data, we're not going to get the best possible images. If we literally fit data and we sample from it, we're going to get things like this. And it still has the outline of what might be an image. So there's more white in the middle and more black on the sides. So it kind of looks like what we want, but it's clearly not anything that's good enough. Okay, so clearly this is too strong. What else can we do? Again, there are entire fields of computer science that study this problem. There's many approaches to this. Here, let's look at one possible approach, which is going to be based on this idea called conditional independence. First of all, what is conditional independence? You should remember this, but let's do a review in 2 slides. We say that 2 events A, B are conditionally independent if the following identity holds. So the probability of A and B given C factorizes out as 2 independent probabilities. This is the general definition for events. Here, we're working with random variables. So for a random variable, we say that 2 random variables are independent if these events, for each possible value of x, each possible value of y, each possible value of z, the events of these specific assignments are independent. That is the definition of conditional independence for random variables. And we can write this in a more compact form as follows. So P of x and y given z equals P of x given z times P of y given z. And we can write this even more compactly. I guess this is an equivalent definition. And we can write this more compactly as x per y given z. So that's one standard piece of notation. Again, I'm going through this quickly because this is standard probability. But if not, please, if you don't remember this, please review the slides on your own and just try to do a little refresher on this. Okay, and now once we know that certain events are independent on each other, there's 2 important rules in probability that we should remember. Again, this is fairly this is the first class in probability, so nothing particularly new, but let's just look at it again. The first rule is called the chain rule, which says that if we have a sequence, if we have a number of events, if we have n events, then the joint probability P of S1 and P of S2, etc., up to Sn, this can be written as probability of S1 times probability of S2 given S1 times probability of S3 given S1 and S2, all the way to Sn given all the previous things. This is called the chain rule of probability. And another important rule is Bayes' rule, of course, which says that if we have probability of S1 given S2, then we can rewrite it in a way that only involves either S1 by itself, S2 by itself, or S2 given S1. So we can flip, if we have S1 given S2, we can flip it to get something, to say something about S2 given S1, plus these other terms. So you can think of Bayes' rule as a way of flipping the conditioning. Okay. 2 rules from probability that you should remember throughout the course. We're going to use them a lot. Okay, and now the idea is that, okay, in our simplifying assumption, we try to make everything completely independent. That's too strong. Something that we can do I guess one modeling assumption that we can make is to assume that things are conditionally independent. So what might that mean? Let's start with this example. So here we have a joint distribution P of x1 and etc. And we could try modeling this. We could try, instead of directly modeling the joint, we could rewrite it as the chain rule, and we could try to then have a model for each term in this chain rule product. So that could be another approach for defining a probability. How many parameters would this have? Exactly, 2 to the power n minus 1, because nothing has changed. I didn't change anything. This is something that's always true. This doesn't introduce any additional assumption. It doesn't restrict the class of probability. I can just take any probability that's a joint, I can rewrite it as the chain rule, and that doesn't change anything, right? I haven't restricted at all the class of probabilities. I haven't restricted at all the set of probabilities by rewriting it in an equivalent way. So that's the same. Again, you need 2 to the n minus 1 parameters, and you can also just check that this is true because, well, we know, first of all, nothing changed. That's one reason. Or you can literally count how many parameters you need on the right. So P of x1, that's just a Bernoulli that requires one parameter. P of x2 given x1 is the Bernoulli over x2, but it's conditioned on x1. So for each value of x1, I have a different Bernoulli. So x1 can take two possible values, therefore I need two values for x1. Similarly, the third term, x1, x2, that's an assignment that takes, those are two Bernoullis. There's four possible things on which you could condition in the third term. For each of them, you have a Bernoulli over x3. So that's 4 parameters you need for the third term, then 8 for the next one, etc. So you get this series, and we know that this sums to n minus 1. So nothing has changed. So the chain rule by itself is not enough, right? Yeah, that's what we just said. So the chain rule by itself does not give us anything. But instead, let's say that we now introduce some simplifying assumptions. So we take the chain rule, and instead of assuming that each variable depends on all the other variables, all the previous variables, let's say it depends only on a small number of these previous variables. Let's say that xi plus 1 condition, it's independent on xi plus 1 given xi is independent of everything that comes before. So in other words, I take each of these terms and so x3 will be only dependent on x2 but not x1. x5 will be only dependent on x4 but not anything that comes before x4. Let's say I make this simplifying assumption. So now I'm assuming something and I'm restricting a set of possible distributions by doing this. So this is what I mean. Here I delete x1, here I delete everything before xn minus 1. How many parameters does this need? 2n minus 1. That's correct. 2n minus 1 parameters for this. So now we have a little bit more parameters. Instead of having just n, we have a little bit more, but we have a more expressive distribution. So playing with conditional independence is a way of allowing us to trade off model complexity with model expressivity and the number of parameters that we need. Those are the two things that we will play with. By making fewer assumptions, the model is more flexible, more expressive, but it requires more parameters. We can trade off between the two by conditioning on either more or less variables. Okay, and this idea is a special case of a more general framework called Bayesian networks. I'm going to assume that some of you have seen Bayesian networks, but maybe not all of you. And if you haven't seen Bayesian networks, no worries. The point is to just get the general idea. But the idea of Bayesian networks is that we can use this. We can use this idea of conditioning not on all the variables in the chain rule, but on a subset to define more restrictive, restricted and tractable probabilistic models. In particular, what you do in a Bayesian network, is that for each variable, you define a set of ancestors. So you don't condition, you start with a chain rule, and then you simplify each term in the chain rule by conditioning not on all of the variables, but on a subset of that, and that subset is called the ancestors of I. In my previous example, we only had one ancestor. So in the very first example, we had 0 ancestors. It was all independent. In the next example, we only had one ancestor, but you can generalize this. You can condition on an arbitrary subset of the previous variables. And that's what happens. So you use this chain rule, except this conditioning term is some subset that you define. And so this is called a Bayesian network, or this type of probability is called it's a probabilistic model that can be expressed as a Bayesian network. That's the high-level idea. That's all that is enough to understand here. This is one approach to having tractable general models that address the curse of dimensionality. It's different from everything that we're going to be looking at in this course. Well, it's reasonably different from what we're going to be looking at in this course, but I just want to point it out that this is the classical approach, and what we're going to be doing, the deep approach, is going to be, in some sense, an alternative. Well, it's going to be not fully orthogonal, but somewhat different from this technique. But let's just remember Bayesian networks as another way of doing what we want to do. There's a question?
So it can be there. I'm trying to think of like it can be variables from. I don't know if that makes sense, the time component, but I'm trying to compare that to other frameworks. But it can be variables that are like after or before. I'm trying to compare that to when there's a sequence model and we say, are we going to condition on like the previous 2, the previous 3, or the previous 4? For Bayesian networks, it can be on an amount of variables, even if it's after or before. Is that it can be any sort of like set, right?
Yeah, it could be any sort of set. I will give you an example in 2 slides. But yeah, maybe the question is, how do you choose which variables to condition on? And I think you said maybe if there's like a time component, maybe you condition on the previous variables in time, or if you have prior knowledge about the problem, you could use that to select which set of variables to condition on. That is the most standard approach, and you can also even try to learn this subset. That's a more complicated thing. Anyway, I'll give you an example in a moment. So one thing though is when we choose these ancestors, we have to be a little bit careful about how we choose them. For example, if we have 2 variables and x1 is the ancestor of x2 and x2 is the ancestor of x1, that doesn't work, right? You can have the probability of x1 comma x2 equals p of x1 given x2 times p of x2 given x1. That doesn't make any sense. So there has to be, it still has to factorize in a way that's conditioned, in a way that gives you a valid probability distribution, right? So if you start with the chain rule and choose a subset of the elements of the chain, if you choose a subset of what you would have conditioned in the chain rule, that is a valid distribution. But in general, like there has to be some, like you can't take a variable and then condition, like you can have an ancestor, you can't condition on an ancestor and then have the same variable again be the ancestor of its own ancestors. Like you cannot have a loop, and you cannot have loops in this process. And so that's why when we talk about Bayesian networks, we also talk about directed acyclic graphs. In Bayesian network can be represented as a graph. So you can represent these ancestry relationships with these variables as a graph, where each node is a random variable, and there's an edge between there's a directed edge between a variable there's a directed edge from the ancestors to their child, and if this graph basically if you have this distribution with ancestors, you form the graph, you draw edges from the ancestor to the children, and this graph has to be a directed acyclic graph. If it's a directed acyclic graph, good, you have a valid distribution. If it's not a directed acyclic graph, then this is invalid. It will not give you a valid distribution. Right. So this is the formalism for a Bayesian network. Yeah. So you can, I guess, one way of defining a Bayesian network is you can start from a set of ancestors, or you can also equivalently define a Bayesian network by drawing a graph. And once you have the graph, you define this distribution where the parents of I or the ancestors of I are the parents in the graph, or the parent nodes in the graph. Let me give you an example. Okay, so first of all, what is a DAG? On the left, that's not a DAG. If the ancestry relationships have a cycle, that's wrong. It's not a valid probability distribution. If there's no cycles, then you have a valid distribution. Here's an example of what a Bayesian network can look like. This is a classical example from a text from the Kohler textbook on probabilistic graphical models. Here, we're trying to model a student that has taken a class, and they got a grade in that class, and they're asking the professor for a recommendation letter. So there's five possible variables that we have. In the middle, we have the grade the student got in the class. That grade is determined by the difficulty of the class and by the intelligence of the student. And the intelligence of the student also determines their SAT score, but that's not directly correlated to the grade. And then the grade determines the letter, right? So these are the five variables that we want to model, and let's assume there's a finite number of values. So the grade can take one of three possible values: G1, G2, G3. Difficulty, we have two difficulties: easy or hard. Intelligence also high or low. I don't know. SAT also good or bad. Two possible outcomes, and then the letter can also be either good or bad. So this is an example where we could apply Bayesian. We could make it a Bayesian network. In fact, this is the graph that is a reasonable Bayesian network. So in particular, the letter is directly determined by the grade, but the letter is probably not determined by the difficulty of the class. Like if the class was easy or hard, here we're assuming that the letter is going to be more likely good if the grade is good, and more likely bad than if the grade is bad. But or I guess maybe the writer of the letter doesn't directly observe the intelligence of the student; they only observe the grade. So this is why it makes sense to define a probability distribution where the letter is only dependent on the grade, but not directly dependent on the intelligence. Or the SAT score is not correlated at all with the letter. So it doesn't make any sense to have any edges between letters, and it doesn't make any sense to have any kind of ancestry relationship between SAT and letter because they're fairly independent. So this is an answer to the question that you had. Maybe this is at least a partial answer. When would you apply this Bayesian network idea? How would you decide what the graph is? Well, you can often look at the problem and you know that two things should obviously not have any dependency on each other. Like the intelligence of the student and the difficulty of the class, that's completely unrelated. So it doesn't make any sense to have a term that has intelligence be a function of difficulty or difficulty be a function of intelligence. They're completely unrelated. So that's what you get. These are the kinds of assumptions you can bake into a Bayesian network by deleting certain dependencies or equivalently deleting certain edges in the full graph. And this requires less variables than we would normally need if we had. So we have 5 variables. Each of them is at least 2, and some of them are. One of them is 3. So that's at least 2 to the power 5 parameters that we need to specify the whole model. But because we have these edges, we only need to specify these tables. So here we need 2 parameters here, 2 here, 4, and 12. 12. So that's much less than the 32 parameters, or more than 32, that we would need to specify the full graph. But the point is, by deleting certain edges or deleting certain dependencies in the chain rule decomposition, you can define a probability distribution. You can define a probabilistic model with fewer parameters that you would have to use if you did the naive thing of just modeling full joint distribution, like a full category. Okay, so this is the distribution. If you think of it in terms of the chain rule, this is the distribution that we're defining. We're defining a distribution over these 5 variables, and when we have this graph, we're assuming that it decomposes in this way. You can always go back and forth between directed graphs and decompositions. You can go back and forth between the two. These are equivalent. This graph is just a visual way of describing this decomposition. And for each valid decomposition, you can draw the graph. And for each valid DAG, you can get a valid decomposition. They're just an equivalent way of describing the same thing. So here we're making the following assumptions in the graph. Okay, so summary so far, we have this problem called the curse of dimensionality. One way to get around it is to assume certain conditional independencies. One way is to define a model where not everything depends on everything else. Certain variables or certain pixels are independent of certain other pixels, conditioned on other pixels. If you make these assumptions, then you can get away with much fewer parameters. Your model is less expressive, like that DAG in that example that I just showed. It doesn't capture all the possible distributions over the 5 variables. It captures a subset of them, but it captures a good subset because the other ones where like intelligence and difficulty have dependencies, those are probably wrong. If we were to learn it, we would want the model to not have any dependencies there. So we can bake in good assumptions into the model by thinking of it as a graph. And that's one approach to solving the curse of dimensionality. And then in the rest of the lecture, I'm going to propose another one, which will be our first example of a naive generative model. Okay. So, but before I do this, I want to do a little detour and talk about discriminative generative models. So I guess first start by talking about generative models. I'm going to assume that everybody has taken a machine learning course before, and you have taken this machine learning course, and there you've seen the naive Bayes algorithm. The naive Bayes algorithm is a simple example of a generative model. So what does the naive Bayes model do? It assumes the following. So here we have an application of naive Bayes to spam classification. Our goal is to classify emails as spam. Y equals 1. Y is the label. So spam equals y equals 1. Spam is y equals 1. Not spam is y equals 0. And then our data x is a bag of words representation of the email that we want to classify. And so what it means is that x, so x is a vector. Each component maps to a word in a vocabulary, and that component xi equals 1 if the word I appears in the email, xi equals 0 if it doesn't appear. So that's the data. X is a binary vector that is a bag of words representation of the email. That's the setup. That's the data. Now we want to define a model, a probabilistic model of this data. The way we do this in naive Bayes is, so we actually form a Bayesian network with the following directed graph. So a naive Bayes model is a special case of a Bayesian network where the graph has this form. So what does it mean? It means that y doesn't have any ancestors, and then each other variable, its only ancestor is y. In other words, if I were to write this out as a conditional, as a product of factors, I get the following. So this joint distribution, normally this would be extremely high dimensional because again we have n is the size of the vocabulary, n is like 10,000. Each xi is a pixel, so we would have 2 to the power n minus 1, and then this y also appears, so we have more than 2 to the n minus 1 parameters. But if we make this simplifying assumption that the distribution has conditional independencies described by this Bayesian network, then this is equivalent to assuming that it factorizes in this form. We're assuming extra conditional independencies, and now the thing on the left becomes our model, the thing on the right becomes our model, and that's the model that we're going to try to learn. Specifically, naive Bayes assumes the following. Well, okay, first of all, these xi given y, they're all, so y is binary, so p of y is a Bernoulli that has one parameter. P of xi given y is also, so it's a Bernoulli for each y. So if you fix y, p of xi given y is a Bernoulli. So P of xi equals, P of xi given y equals 0 is a Bernoulli that is one parameter. P of xi given y equals 1 is another Bernoulli that requires another parameter. So here we have one parameter for y, and we have 2n parameters for the other components. So this thing has 2n plus 1 parameters in total. And so we assume this particular form. We can learn these parameters from data using maximum likelihood, like we did, for example, in applied machine learning in fall. And now we have a probabilistic model. And if we want to make predictions, we can apply the following formula. This is just Bayes' rule. Remember Bayes' rule from a few slides ago and earlier, hopefully. And also remember, I said that a generative model can do everything that a discriminative model can do, including prediction. So here, even though I have a distribution over x's, I can flip the distribution. So yeah, I can flip the distribution to get P of y given x. Or equivalently, if I want P of y given x, I can flip it to get something, a formula that only involves P of y and P of x given y. So that's the formula. I'm not going to go into details, but this is just a straightforward application of Bayes' rule that we've seen in applied machine learning last semester and in any machine learning course. You should see this. Yeah, so this is the model. Now, of course, some of these assumptions are sometimes wrong. So in particular, Bayes has this problem of double counting the evidence. If two x's are closely correlated, then we might count them twice towards the evidence. So it gives us probabilities that are a little bit overconfident, underconfident. But in practice, this works quite well. And it's also very fast to train. If you remember, if you wanted to learn the x's with a closed form formula for each parameter, so this is very convenient for many reasons. This is actually a very, very strong baseline for text classification. Okay, so that's an example of a generative model. Now, another way of approaching this time classification problem is to use the discriminative model. Suppose that all we need for predictions is P of y given x. Our approach was to learn P of x given y and P of y, and then flip them to get P of y given x. So in some sense, we're doing more work. If we only need P of y given x, why are we doing all of these things? Let's just model P of y given x correctly. Let's just learn this distribution P of y given x, and effectively previously our Bayesian network had this form, and now it will have this form in a discriminative model. So y will be dependent on x. This is going to be called the discriminative model because it is only useful for discriminating y's given x. It doesn't do any of the things that generative models do. It doesn't do generation. It cannot deal with missing inputs. If the only thing you want is to predict P of y given x, then let's try to form directly a model of P of y given x. So what does it mean to form a model of P of y given x? Well, an example of this is the logistic regression algorithm. In the logistic regression algorithm, or I guess in various types of discriminative models, we assume that P of y equals 1 given x is given to us by some formula f of x and some parameter alpha. So this formula it takes as input the x on which we're conditioning and some set of parameters, and this formula f spits out a probability of y equals 1. So it's f of x and alpha spits out a prediction or spits out a probability between 0 and 1. It's interesting that this is not a table anymore. Previously, in all of our examples, all of these generative models, we were effectively representing them as tables. Even in the DAG example, it was we had a table for each node in the DAG. Similarly, for the Bayesian network, we have for the Naive Bayes example, we have essentially a table. Everything is this complex. Here, this is a slightly different approach. We just assume that we have some formula. The formula has some parameters alpha, and we just learn the parameters alpha that produce good results when we plug them into the formula. And so what's interesting with this approach is that it doesn't depend on the complexity of, on the size of X anymore. It only has this fixed set of parameters, so the dimensionality is fixed to the number of parameters that we choose, right? If we have D parameters, then we have D dimensions. And our main constraint is that the output of F has to be between 0 and 1, and it has to depend in some reasonable way on x1 and xi. By reasonable, I mean it has to make good predictions, and it still has to be tractable. So one way in which we could do this is, and this is what linear regression does, is that we could have a linear function of the parameters, of the input x. So we have alpha, we have x, we can take the dot product with alpha and x, we can make alpha be a vector of the same size as x, and we take the dot product, we call the thing z of alpha and x, and that's the formula. That's maybe the simplest way in which we could define something which looks like this formula, f of x and alpha, which is the dot product. The problem with this is that z is not between 0 and 1, and we want f to output a probability, so it has to be between 0 and 1. So what we do in logistic regression is that we pass z through this sigmoid function, and the sigmoid function takes the real number and squishes it between 0 and 1. And now this, so sigma of z of alpha and x, that's what we define our f. That's what logistic regression defines f. And this is now an example of a generative model. Here, this is an example of the sigmoid function. It takes a real number, it squishes it between 1 and 0. And on the left is an example of a Bayesian network that could be associated with this distribution. Note that there could be a bunch of edges between the x's. We haven't made any simplifying assumptions at all on dependencies between the x's. But we don't care because the x's are always observed. So we never have to worry about these interactions. The x's are always fixed, and we don't really care about forming a distribution over x, so it doesn't matter if they're all correlated. We only care that y given x is simple. Okay, so if we were to visualize it, if we were to visualize this model, we get something like this. So here we have a two-dimensional x, and this heat map shows the probability in different regions of the space of x. So this is a heat map or contour map on the left, and on the right is the three-dimensional version. So it assigns higher probability to spam in the yellow region and a low probability in the blue region. And as we go from blue to yellow, it changes its point. And then the decision, if you wanted to make this for, if you wanted to make this a predictive model, if you wanted to use this for classifying spam, we would take the line where the probability equals 0.5, and that would be the boundary where we would decide whether it's spam or not, depending on which side of the boundary the data points are. Or in the language of probability, if p of y equals 1, x and alpha, given x and alpha is greater than 0.5, then it's lying on the spam side of the boundary. Then x is lying on the spam side of the boundary, so we predict this to be spam. Okay. But note that by making this linear assumption, we're also making a particular assumption on the probability. In particular, we're assuming that the probability is this thing which changes as we move perpendicularly to the decision boundary. It changes with a certain probability, changes from 0 to 1 at a certain rate that's defined by this sigmoid. So that's an extra assumption that we have made, that we have baked in when we chose this linear model in the sigmoid. So choosing this parametric form also restricts the probability function. In practice, they don't have this double counting problem to which I briefly alluded to. And in practice, if you have a lot of data, the discriminative model will often work better for predictive modeling. In fact, most of the popular algorithms that we use for prediction, for classification, are instances of discriminative models. Even these deep neural networks, so a deep convolutional neural net is another case of this where this f is now a different form. If you make f a conv net, then that's a different type of model, but they're all instances of discriminative. models. Discriminative models are very powerful, but generative models are also very useful because we can model X. We can do things like handling missing data, or if we see, so if we have a partially observed X, we can still make predictions from the model, and we can also do things like generation and other tasks that we can't do otherwise. So generative models are also useful. And in particular, generative models can become especially useful if we combine them with certain ideas from discriminative models in deep learning. And this is what I want to end the lecture with. So far we've seen Bayesian networks as one way of defining a probability over data. We've seen these parametric discriminative models as another way of defining a predictive distribution of y given x. And in the last few slides, I want to hint at how we can combine these ideas and get the best of both worlds. And this will also hint at our first example of a deep generative model, which is going to be an autoregressive model. Okay, so remember that in discriminative models, we assume this particular form of y given x. And the example that I just gave you, linear regression, this example assumes that f here is a linear function with a sigmoid on top. So it assumes a simple form. You can also make this more sophisticated by assuming a more complex form on f. Let's say that f has the following structure. So we take x, we multiply it by a matrix A, we add a binary B, and we add this nonlinearity G. We call that whole thing H of A, B, and X. And then we apply alpha not on X, but on H of A and B of X. As you can see, this is just a fully connected neural net whose hidden layer is H. Right? So instead of making f a linear function plus a sigmoid, we can make it a fully connected neural net with a single hidden layer, which is H, and that's what is exactly described by this formula. This is now a more expressive model. It has more parameters, and the hope is that it can model more expressive, more flexible distributions. So we have increased the set of all the possible distributions that we can approximate using this model. Right, so now we have a nonlinear dependence. Again, main advantage is it's more flexible. Main disadvantage is that it has more parameters. And we can keep repeating this process many times. So we have one H, but we can have multiple H's, and this gives us a neural network which has this particular form. Let's now compare all. So okay, I guess now we have three possible approaches. We have Bayesian networks, which are derived from the derived from the chain rule, conditional independence. We have these simple linear models, and we have these neural models. Let's compare them. In fact, let's see if we can combine them. So the original way, the initial model family or one of the first model families we looked at was something that's based on the chain rule. So if we have a distribution over these 4 pixels, we form all the conditionals in the chain rule, and we try to define a model for each condition. This is still exponential with the number of pixels. It doesn't gain us anything. So one way that we use to simplify this model is we remove certain dependencies, and this is the BaseNet approach. Now, imagine what would happen if we instead added the neural approach to this setting. So each pixel here, x3, that's just a binary that's like a binary variable, 0 or 1. So each of these terms, x3 given x1, x2, x4 given x1, x2, x3, these are all each term here, x4 given x1, x2, x3, these are exactly the same type of model that we try to solve using logistic regression or using discriminative neural networks. x4 given x1, x2, x3 is just a predictor for the 4th pixel given the previous pixels. This is a binary classifier in some sense. This is a probability that tries to model the probability of x4 being black or white given the previous pixels. So because this is literally the same problem we just tried to solve using that logistic regression model and using that neural net model, we can also apply a different technique. And instead we could try to so instead of simplifying these conditionals, we could try to leave them unsimplified, but instead we could approximate them using a neural model. So in the naive approach using the chain rule, we kept all the conditional and all the dependencies, but we tried to, but then we left each conditional unsimplified. We left it as a full table that describes all the possible assignment, that it has a probability for each possible assignment of x4, x1, x2, x3, and that's just exponential. So one way to reduce this, one way to deal with this curse of dimensionality is to reduce the number of terms in the table, which is what the Bayesnet is doing. Another approach is to not model a table, but instead replace the table with a parametric model, like a neural net or a logistic regression. And that's what the neural approach is doing. So one way in which discriminative models and neural networks can be combined with generative models is this idea of modeling conditionals as neural nets. And once you do this, you can also have fewer parameters because now each of these neural terms doesn't need, right? If we make this logistic regression, if each factor here is approximated with logistic regression, well, that has a linear number of parameters. So it has at most n parameters, and there's at most n terms. So there's going to be less than n squared parameters in this model. So this is an important point. Another way in which we can get a compact model for a high dimensional distribution is to take the chain rule, and instead of deleting terms in each factor, we keep all of the terms, but we approximate the entire factor using a parametric model. And that's the first approach that we're going to take in this class to building a deep general model, in particular in other regressive models. And this can be a powerful approach because if these neural nets are expressive, we might be able to approximate this distribution very, very well from data without having to start by deleting. And also, I want to mention this extends to continuous variables as well. So far, I've been talking about speed variables in the entire lecture. But if we have a continuous variable, well, we can't represent it as a table anymore, but we can assume a certain parametric form, like a Gaussian, which you see here and which you should remember for the other lectures that are coming, for a uniform distribution, or a Poisson, or a gamma, or any sort of distribution. And if we have a continuous random vector, we can also represent it using a density function, a joint density function. We could assume some kind of parametric form, like a Gaussian, or we could also form a chain rule over a joint. So if we have three continuous variables x, y, and z, we can still apply the chain rule in this form. And now this is a product of densities. And similarly to how we approximated each conditional factor with how we propose modeling each factor using a neural net on the previous slide, we could also model each factor here using a neural net, and the same slide will apply. Okay. And then using this approach, we could define some interesting classical models. So for example, one type of model, which we're going to see, which is called a variational autoencoder, can be seen in a special case of this, where we have two variables, z and x. We can factorize them in this form. One easier setting than what I'm proposing is just a mixture of two Gaussians. Let's say that z is a Bernoulli, 0 or 1. In a regular mixture of Gaussians, we have a density which factorizes in this form. We have z is a Bernoulli, then x given z is one normal, x given z equals 1 is another normal. It's just a mixture of Gaussians. We could also instead assume that z is coming from some continuous distribution, and x given z could be be a normal distribution, whose mean is this can be seen as an infinite mixture of captions. And then something that we're going to do in this course is that we're going to, instead of just having this mean be a linear function of z, we could make this function be some kind of complicated neural net approximator that takes z as input and spits out mu, and this will give us another type of models that we're going to see called radiation model models. Okay, so these are some examples of generative models that are coming in the next few weeks. And next week, we're going to look at autoregressive models, which are going to be an instance of the first approach of modeling factors using neural nets that I just proposed.